I am Mr. P. Mabu Hussain, Assistant Professor of EEE from Institute of Aeronautical Engineering, Hyderabad. In the previous lecture, we discussed about the capacitance of a single phase line. Now, in this video, we are going to discuss about the capacitance of three phase line with symmetrical and asymmetrical spacing of conductors. So, if you see the learning outcomes of this lecture, by the end of this lecture, the students will be able to develop the expression of capacitance for a three-phase line with a symmetrical spacing of conductors, as well as develop the expression for capacitance of a three-phase line with the asymmetrical or unsymmetrical spacing of the conductors. As you already know, what is spacing between the conductor, whether it is symmetrical spacing or asymmetrical spacing. In a symmetrical spacing of conductors, if you observe the distance between any two conductors, so if you are having a three-phase transmission line in which three conductors are there, now these three conductors are numbered as 1, 2, 3. Right now, the distance between any two conductors will be the same in a three-phase symmetrical line. So this is the symmetrical line. So if you observe all the distances between any two conductors, the distance is same. So this type of transmission line is called a symmetrical transmission line. So in which the conductors are spaced equilaterally. Now asymmetrical or unsymmetrical transmission line in the sense, so the distance between any two phases, if you observe, that may not be the same. Right? So if you take again three conductors, 1, 2, 3. So here the distance between 1 and 2. So you may be represented with D1. So between 2 and 3, you can represent with D2. Between 3 and 2, you can represent with D3. So now if you observe all these distances, so these distances will not be the same. Okay, so this type of transmission line is called the asymmetrical transmission line or unsymmetrical transmission line. Okay, now we are going to develop the expression of capacitance for both of these two lines, right? Symmetrical lines as well as asymmetrical or unsymmetrical line. Okay, so let us first see the capacitance of three-phase line with the equilateral spacing of conductors, or you can also say it as symmetrical spacing of conductors. Here, if you observe the figure here, now in this figure, there are three conductors named A, B, C. So A, B, C are the three conductors, and the distance between any two conductors is represented with capital D here. Right? So distance between any two conductors here is the same. So this transmission line is a symmetrical transmission line. Right? Now here we are going to develop the expression for capacitance, and the capacitance, if you see, capacitance will be equal to Q by V, right? Charge per voltage. Right? Once if you want to calculate the capacitance of any transmission line, so then you need to find out the potential difference between the two lines. Right? So potential difference between the two lines you need to find out. So then you can easily find out the capacitance. Okay, so now before we are finding the capacitance between any two transmission line conductors, you need to take some assumption, right? So the first assumption is that here the conductors are far away from the ground, right? So all the three conductors in a transmission line system are such that if you see the distance from ground to the conductor distance, distance must be very high. So that means the clearance between the conductor and ground, that must be high. So that we can neglect the effect of earth here. Okay. So second assumption is that conductor radii, if you observe, this conductor radii must be smaller than the distance between any two of conductors. So that means the radius of conductor is represented with smaller. So then the distance is represented with capital D. Right? Now this radius must be smaller than the distance capital D. Okay. Another assumption here is that the charge on the conductor, charge here is represented with charge Q. Okay, the charge on the conductor is uniformly distributed along its length. Right? So charge on the three conductors if uniformly distributed, so then in such a case this equation will hold good. So that means the sum of all the charges in all the three transmission line must be equal to 0. So QA plus QB plus QC is equal to 0. Right? So now in the previous video we discussed that the general equation to determine the potential difference between any two conductors in a group. Suppose if you are having a group of conductors here, now in this group of conductors, now the potential difference between any two conductors in this particular group you can determine by using this expression. Right? The derivation for this expression we already discussed in the previous lecture. So if you want to know how we got this expression, you can watch the previous video. Okay, so you have to remember this equation, right? So which represents the potential difference between any two conductors in n number of group of conductors. Here capital N represents the number of conductors in this particular group. Okay, if you are having n number of conductors in a group, so then the potential difference between any two conductors in that particular group will be represented with this equation. Okay, so here the equation is VKI. So Ki in here is nothing but the conductors between which we are going to calculate the potential difference. So here this conductor we call it as K, this conductor we call it as I. Now we are going to find out the potential difference between K and I in this n number of group of conductors, right? So the value of VKI so will be equal to 1 by 2 pi epsilon naught summation of m is equal to 1 to n. So capital N here is the total number of conductors in a group. So in QM ln DIM by DKM. So here you see here. So this is DIM by DKM. So in the numerator you are having this term I term, and the denominator you are having the K term. Okay. So you observe that from this equation only we are going to develop the capacitance voltage difference between any two conductors in this three-phase transmission line also. Right. So in this three-phase transmission line, how many number of conductors are there? 3. Right. So N is equal to 3 here. Right. So these conductors, instead of representing with the numbers here, they are represented with the letters A, B, C. Conductor A, conductor 1 is A, conductor 2 is B, conductor C is 3 is C. Right. Instead of giving numbers, they are represented with the letters. So here the value of N here is nothing but you can take A, B, C. So this will be the 3. Okay. So that means here that value of M. So the value of M will be going from A to C. So A comma B comma C, like that you have to consider. Okay. So now if you calculate the potential difference, so between the conductors A and B here, so between these two conductors, so if you want the potential difference equation, so then from this equation how you can write? So VAB is equal to, so VAB is equal to 1 by 2 pi epsilon naught sigma. So here M is equal to 1 to N, here it is there, right? So this 1 to N you have to take whenever the conductors are represented with numbers. So but here the conductors are represented with letters A, B, C. So here you have to consider M is equal to A to C. So that means M will be A, B, C can take. So now QM by QM into ln DIM by DKM. So here I is nothing but B here. So this will be DBM. AK is nothing but A here. So this will be DAM. So this equation you will is the potential difference between the conductors A and B. So that is written here. So VAB is equal to 1 by 2 pi epsilon naught into I will write here VAB is equal to 1 by 2 pi epsilon naught sigma M is equal to, here once you have to take A to A, B, C, Q, M ln D, BM by D, AM. Okay. So now here M you have to substitute A here. So once, so then B, then C. Right. Then you can write this equation VAB is equal to 1 by 2 pi epsilon naught. If you substitute M is equal to A, then this equation can be written as QA ln. So distance from B to M. If you see here, so distance from this can be written as I will write again here VAB is equal to 1 by 2 pi epsilon naught into, if you substitute A here, this will become QA ln D BA by D AA. Okay. So plus if you substitute B here, so then you will get QB ln D BB by DAB. Right. Then if you substitute C here, QC ln D BC by DAC you will get. So this is the voltage equation. Right. From this equation we are getting this equation total. Right. Now if you see here, DBA is nothing but the distance between B to A. So which is D here. So dBA you can write it as D here. Now you will get this equation. So VAB is equal to 1 by 2 pi epsilon naught QA ln, in place of dBA you will get D here. Okay, and the distances, self distance of DAA, DBB and DCC if you get, so then that value is always equal to radius of the conductor. Okay, so DAA here you are having, so in place of DAA you can write R here. Okay, so plus, so then QB ln, so DBB, in place of DBB you can write radius, and DAB is the distance between A to B, which is D here, plus QC ln, so DBC here is nothing but B to C distance, which is D here, by DAC distance also same as D only, so D you will get. Okay, so finally you are getting the potential difference between these two conductors A and B will be equal to 1 by 2 pi epsilon naught QA ln D by R plus QB ln R by D plus QC ln D by D you are getting, right? So from this DD you will get, you can get cancelled, and ln 1 you will get, this entire value will become equal to 0. Okay, so this can be written as VAB is equal to 1 by 2 pi epsilon naught QA into ln D by R plus QB into ln R by D. Okay, so this is the potential difference between the conductors A and B. Right. Similarly, if you want to develop the potential difference equation between the conductors A and C, how you can write? Right. So we are going to develop the equation for potential difference between the conductors A and C here. Okay, so this is represented with VAC. That VAC is equal to, how you can write, 1 by 2 pi epsilon naught sigma m is equal to A comma B comma C QM ln D. So first here this C you have to consider D CM by then this A. So D AM. Okay. Now if you expand this, how will get? VAC is equal to 1 by 2 pi epsilon naught. If you substitute M is equal to A, so then QA ln D CA by D A. Right, DAA will get. Okay, so plus if you substitute M is equal to B, so then QB ln D CB by D AB will get. If you substitute M is equal to C, so then you will get QC ln D C by D AC you will get. So this is the voltage equation between the conductors A and C. Now here this can be written as this equation. How you can see here. So 1 by 2 pi epsilon naught, 1 by 2 pi epsilon naught. So here it will be the same. So then QA ln, so distance DCA. So DCA here is nothing but capital D. So this is capital D, and DAA you have to write equal to radius of the conductor. So D by R will get, plus QB into ln. So the distance between C to B and distance between A to B, both are equal to capital D only. So here the second term you will get ln capital D by capital D plus QC ln, this DCC is nothing but R here, by DAC is capital D. Right. So this equation you will get. Now here also you are getting a numerator and denominator in the second term same, so which is capital D. If you get cancelled, you will get ln 1. So this value will become equal to again 0. So from this, what you can write, VAC is equal to 1 by 2 pi epsilon naught QA ln D by R plus QC ln R by D you will get. Okay, so VAB is this equation, VAC is this equation. Now we are going to add the both voltages VAB and VAC. Right, if you add both the equations, what you will get? Let us see here. So this term is 0 and this term is also 0 here. So if you so here in place of K, you assume that this value is epsilon naught. Okay, So this always you consider that k is nothing but here epsilon naught. So in some textbook, instead of representing epsilon naught, they represented with the k, right? So this k is nothing but permeability. So which is represented with this epsilon naught, permittivity. Sorry. Okay. So this VAB plus VAC, now we are adding these two, right? So now in the both the term, you are having the 1 by 2 pi epsilon naught. It will be the common. So then you see in the first term, QA is common. So QA ln d by r is there plus QA ln d by r. So if you add these two, you will get 2 QA ln d by r plus. Now if you see here, so this term is 0 and this term is 0. So now, so if you add these two terms, what you will get in these two terms, ln r by d is common, and when you take ln r by d as common, you will get QB plus QC. Okay. Now, as you know, as the charge is uniformly distributed in the transmission line system, so QA plus QB plus QC, QA plus QB plus QC, this value is equal to 0. So from this equation, you can write this QB plus QC is equal to minus QA. So now in place of QB plus QA, so you can write minus QA. So here in place of QB plus QC, you can substitute minus QA. Okay. So now VAB plus VAC is equal to 1 by 2 pi epsilon naught into 2 QA ln d by r plus minus QA ln r by d you will get. Okay. So now in the both the terms, you will be having the QA term as common. Okay. So you can take it out also. So then what you will get? So VAB plus VAC, right? So here I will write again by erasing all this. Okay. So this equation, now you can write it as 1 by 2 pi epsilon naught into 2 QA ln d by r plus, in place of this QB plus QC minus QA, you can write minus QA ln. So this ln r by d, so this can be written as minus ln d by r. Okay, in the reverse we can write. So this can be written minus ln d by r. Now this minus will become plus again. So this will be equal to 1 by 2 pi epsilon naught 2 QA ln d by r plus QA ln d by r. So now here if you add these two, you will get 3 QA ln d by r by 2 pi epsilon naught. So which is the value of VAB plus VAC, right? VAB plus VAC is equal to 3 QA by 2 pi epsilon naught ln d by r. So this is the sum of potential difference between conductors A and B and conductors A and C. Okay. So now if you remember that transmission line system, VAB is nothing but it is the difference of two voltages, so phase to neutral voltages. So VAB is equal to VAN minus VBN, and VAC is nothing but VAN minus VCN. Okay. So difference of the phase voltages between A and B will be VAB, and difference of phase voltage between A and C will be your VAC. Okay. Now what is this VAN? What is this VBN? What is this VCN? You should know. Okay. So VAN, VBN and VCN. So these are the per phase voltages. So in a three-phase system, you will be having 3 phases, right? So in 3 phases, if it is balanced, then magnitude will be the same, right? Out of all the 3 phases, one phase you can consider it as the reference phase. So if you consider VAN, which is the voltage in phase A as the reference, this can be written as VAN at an angle 0 degrees. Okay, in a 3-phase balanced system, magnitudes will be the same. So VBN also will be same as the magnitude of VAN. VCN also will be the same as magnitude VAN. So, but if you observe the angle, this VBN will be lagging the VAN by minus 120 degrees. So VCN will be lagging VAN by minus 240 degrees. This is how you can represent the 3-phase system, right? You already know from the network theory. Okay, this we are going to use in our derivation. Okay, so VAN is which is the phase voltage, VAN at an angle 0 degrees, and VBN is VAN at an angle minus 120 degrees. VCN is VCN at an angle minus 240 degrees. All the phase magnitude of voltages will be the same, VAN only. Okay, so now here you need to find out these differences. Okay, VAN minus VBN, right? So that you will get VAB. Okay, you see here, so VAB plus VAC, so VAB plus VAC we are going to write. So this value can be written in place of VAB, you can write this VAN minus VBN, plus in place of VAC you can write this, which is VAN minus VCN. Okay, so this can be written as, so here we have VAN, so this will be 2 VAN minus VBN minus VCN. Okay, right. So now if you write this 2 into VAN minus VBN is nothing but VAN at an angle of minus 120 degrees minus VCN is nothing but VAN at an angle of minus 240 degrees. Okay, so now this can be written as, if you can take VAN as common in all the terms, VAN into 2 minus 1 at an angle minus 120 degrees minus 1 at an angle minus 240 degrees you will get. Okay, so now if you do the calculation for this, you will get the value will be equal to 3. So this will be equal to 3 VAN, right? So you do with your calculator and calculate this value, 2 minus 1 at an angle minus 120 degrees, 1 at an angle minus 240 degrees, right? So if you calculate this value, you will get this total will be equal to 3. So VAB plus VAC will be equal to 3 VAN. Okay, so in place of VAB plus VAC you can write 3 VAN, right? So this equation here, in place of VAB plus VAC you can write 3 VAN. So 3 VAN is equal to 3 into QA by 2 pi epsilon naught ln D by R you will get. Okay, so here 3 will get cancelled. So VAN is equal to QA by 2 pi epsilon naught ln D by R you will get. So this is the potential difference between phase A and neutral, so which is called the per phase voltage. Okay, right. So you got VAN is equal to QA by 2 pi epsilon naught ln D by R. Now if you want to know the capacitance of the line to neutral, so capacitance of the line to neutral, which is represented with CN, okay, which is the per phase capacitance. CAN you can write. Okay, CAN, why? Because we are writing the capacitance for phase A. CAN is equal to QA by VAN, charge per voltage. Okay, so now this QA by VAN, so this value from this equation you can write. Okay, so VAN here is QA in QA by 2 pi epsilon naught into ln D by R. So this QA get cancelled, so that you will get you will write it as 2 pi epsilon naught by ln D by R. So this is the value of per phase capacitance for a 3-phase symmetrical transmission line. Okay, so CAN is equal to 2 pi epsilon naught ln D by R. Okay, as the transmission line system is symmetrical here, the value of CBN, the value of CCN also all will be the same, which is 2 pi epsilon naught by ln D by R. Okay, this is also 2 pi epsilon naught by ln D by R. So this is how you can determine the capacitance of a transmission line system. Okay, right. So if you want to convert the CAN value, so which is 2 pi epsilon naught by ln D by R here. Okay, so this is values in Henrys per meter. Okay, so units are Henrys per meter. Now suppose if this ln is nothing but log to the D by R to the base E, right? Now suppose if you want to convert this into log to the base 10 and this millihenries to millihenries and kilometers to meters to kilometers, then you will get this equation. Okay, Cn is equal to 0.0242 by log D by R to the base 10 here, right? And the units are microfarads per kilometer. Okay, So you can remember either this equation or this equation for solving the problems. Okay, I feel it. This equation is good for remembering. So VAN is equal CAN is equal to 2 pi epsilon naught by ln d by r, which is in Henry's per meter. Sorry, this is in capacitance, right? So capacitance is always represented with farads. So this will be the farads per meter. Okay, right. Once you know the capacitance here, so then charging current, so which is flowing in the line A. So charging current, so in line A can be written as IA is equal to VA by X of your line A. Okay, so VA by X you can write. So this can be written as VA by, so 1 by omega C AN. Okay, so this can be written as omega into CAN into VA. Okay, VA here is nothing but per phase, VAN how to consider. Okay, so this this can be written as this. Okay, this is a complex quantity, and this current is lagging the reference with 90 degrees. So you can represent with J here symbol. Okay, right. IA is line charging current. IA is equal to omega into CAN into VA. So by using this equation, you can find out the charging current. Okay, so this is how you can determine the capacitance of a three-phase transmission line for a symmetrical line. Okay. Right. Now let us see the capacitance of three-phase line with unsymmetrical spacing of the conductors. Right. In a unsymmetrical spacing of conductor, in the sense, so if you observe the distance between any two conductors, that will not be the same. Okay. So now if you derive the capacitance value for this transmission line system, so then in all the phases you will get a different value. Right, when all the phases are having the different value of capacitance, at the receiving end we will get the unbalanced voltages or unbalanced currents we will get. So because of that reason, to overcome that, in a unsymmetrical transmission line, we always transpose the conductors at regular intervals. Right, so here if you see, this represents the a fully transposed three-phase transmission line system. Okay, what do you mean by transposition? You already know from while deriving the inductance expression for a unsymmetrical transmission line. So the transposition of conductors is nothing but the conductors will change their position at regular intervals, and at regular and equal intervals you have to consider. Right. So if you take a transmission line system which is having the length L, so this will be divided into three sections of equal length. So L by 3, L by 3, L by 3. Now suppose if conductor A and conductor B and conductor C, so all are having their respective position 1 and 2, 1, 2, 3. So A is in 1, B is in 2, C is in 3. Right. So now after the first section, this conductor A will occupy the second position, conductor B occupy the third position, and conductor C will occupy the first position, like this, up to another L by 3 distance. So then after going to L by 3 distance, conductor A will occupy the third position, and conductor B will occupy the so this is A, this is C, and this is D. So this conductor B will occupy the first position here, and conductor C second position, like this. So this is one completed transposition cycle. Okay, when you transpose the conductors, then the capacitance values and inductance values will be the same in each phase. Right. Now let us determine the per phase capacitance for this type of transmission, which is a unsymmetrical transmission line, in which all the distances, if you observe between any two conductors, that will not be the same. Okay, here also for calculating the capacitance, we are going to assume certain points. Right. So the first point is the capacitance the conductors are far away from the ground. Right, here all the conductors you have to assume that they are far away from the ground, such that effect of earth will be neglected. And the second assumption is that conductor radius R must be less than the distance between any two conductors. Okay, and third one is the charge on the conductor must be uniformly distributed, and the charge is distributed uniformly across all the three conductors. So then the sum of all the charge values will be 0 for a three-phase balanced system. Okay, so for a three-phase balancer system, the sum of the charges QA plus QB plus QC, so that value must be equal to 0 here. Okay. Now, in a similar way, you have to recall the general equation to determine the potential difference between the two conductors in a group of conductors, which is Vk is equal to 1 by 2 pi epsilon naught. Right here, in place of epsilon naught, you can even write the epsilon. So if the medium is not known, if the as the overhead transmission line medium is 8, so we are considering mu value will be equal to 1, so that mu will be this value will be mu naught into mu. So this value is 1. So in place of that, you can write epsilon naught. Okay, so this is epsilon, right? So 1 by 2 pi epsilon naught into sigma m1 to n qm ln dim by dkm. So this is the general equation to determine the potential difference between any two conductors in n number of group of conductors. Okay, so here in a three-phase transmission line system, you are having only 3 conductors which are represented with the A, B, C. Okay, and in a unsymmetrical transmission line, we are using the transposition, right? So that means this transmission line will be divided into 3 equal distances, L by 3, L by 3 and L by 3, right? Now here all the 3 conductors will occupy the original position of each and every other conductors, right? So the conductor A will occupy the position of other conductors in a complete transmission cycle. Okay, B also will occupy the other conductors position in a complete transmission cycle. So similarly C also. Okay. Now, for this case, if you want to determine the potential difference, you have to determine the potential difference in each section. Then you have to take the average. Okay. So, potential difference between the phases A and B. So, between these two pages, we are calculating the potential difference. Right. So, VAB in section 1, we are first finding. Okay. So, VAB in section 1 will be 1 by 2 pi epsilon naught QA ln D12 by R plus QB ln R by D12 plus QC ln D23 by D31. You will get this. How you will get this? So from this general equation. Okay. So from this general equation, if you write VAB in section 1. Okay. So right. So this value is equal to 1 by 2 pi epsilon naught sigma m is equal to, here the conductors are 3 conductors which are represented with ABC. So here you have to consider m is equal to ABC. Right. So QM B. So here this I is nothing but this value. Here that I is replaced with B. So this BM by. So K is replaced with A. So D A. Okay. So VAB in the first section, if you want to write, so that value will be 1 by 2 pi epsilon naught sigma m is equal to ABC QM QM into D BM by DAM. So this even can be written as 1 by 2 pi epsilon naught. We expand this Q by considering m is equal to A. So then m is equal to A, then this can be written as QA. So this is ln. Okay. So ln D BA by D A. Okay. So plus QB. So if you consider m is equal to B, so then QB ln D BB by D AB. Okay. Plus if you consider m is equal to C, so then QC ln D BC by D AC you will get. Okay. As I already told, so this value of DAA, DBB and DCC, these distances must be equal to radius R. Okay. So now this is the VAB expression. Okay. So it may be in first section or it may be any section. So this is the equation what you get from this general equation. Now if you observe the first section now, okay, in the first section what you will get. Okay, so VAB in the first section if you write, so VAB in the first section. So in the first section, first this value will be the same, which is this value 1 by 2 pi epsilon naught, right? 1 by 2 pi epsilon naught into, so then, so this QA ln DBA by DAA you are having. So in place of DAA, you can write R. Okay, in place of DBB also you can write R. Okay, now what is the distance from B to A? Okay, so B to A distance is this distance, which is between the positions 1 and 2. So this can be written as D12 or D21. Okay, so that we are going to write here. So D12 by R plus, so then the second term is QB ln, so DBB is replaced with R by DAB. So DAB distance is same as DBA distance, which is again same D12 only. So for the second term QB ln R by D12 you will get, plus for the third term, if you observe, third term QC ln DBC by DAC. So BC distance is this distance, which is D23. Okay, so D23 is the BC distance. AC, if you see, AC is nothing but this distance A to C, so which is D31. So BC can be replaced with the D23 by D31. Okay, so D23 by D31. So this is in the first section, value of VAB in the first section, right? So then in the second, similarly in the second section, how you can write this? So VAB in the second section, right? So in this second section, the distances may be changed here. Okay, so if you write the same equation, so for the second section, so VAB is equal to 1 by 2 pi epsilon naught. So as it is you will get. So then, so first term QA ln DBA by R, right? QA is as it is you can write ln DBA distance in the second, if you observe, B to A is this distance. Okay, so this distance is D23. Okay, so QA ln D23 by R you will get. Okay, QA ln D23 by R you will get, plus second term if you write, so in the second term QB ln R by DAB. So right, R by DAB distance, DBA distance both are same. Again, DAB distance is D23 only. So QB ln R by D23 will get, plus, so for next, the third term will be QC ln DBC by DAC. So now DBC distance is this distance, which is D13 or D31. Okay, and DAC distance is this distance, which is D12. So here 1 and 1, 2, 3 are the positions now. So 1, this is first position, this is second position, this is third position. So DBC is the D13 and DAC is the D12. So this equation can be written as QA ln, in place of DBC you can write D13, in place of AC you can write D12. So you will get third term as QC ln D31 by D12. So this is the value of potential difference in section 2. So now in the same way, the value of VAB in section 3 also you can write from the same equation. So which will be equal to 1 by 2 pi epsilon naught. Now the first term is again QA ln DBA by R. Right, DBA here in the third section is, so B to A distance is this distance, which is D13. Okay, this is 1, this is 2, this is 3. Right, D13 here. So QA ln D13 by R you will get. So D13 and D31 both are the same. Okay, so QA ln D31 or D13 you can write. So by R you will get, plus QB ln R by the same expression you will get. So DAB again. So DAB distance is again same as D13 or D31, plus QC for third term is this one, QC ln DBC by DAC. So DBC distance if you see, B to C distance is this distance D12 and AC distance is this distance, which is D23. So D12 by D23 you have to write. So the value is QC is equal to QC ln D12 by D23. So this is the potential difference between the conductors A and B in each section. Okay, in section 1, in section 2, in section 3. Now the total potential difference VAB, you can write it as average of all these potential difference. That means VAB in section 1 plus VBC in section 2. Sorry, VAB is the same value. VAB in section 2 plus VAB in section 3 by 3. So this will be the potential difference VAB between the conductors A and B. Right? So VAB is equal to 1 by 3 into VAB into V in first section plus VAB in second section plus VAB in third section. Right? We are going to add all the three values. Okay. So now see here. So in all the term 1 by 2 pi epsilon naught, 1 by 2 pi epsilon naught, 1 by 2 pi epsilon naught. All will be having the same term. You can take it out. Okay, so this value will be 1 by 2 pi epsilon naught. Okay, so 1 by 3 you are having here. In all the terms, you will be having again 1 by 2 pi epsilon naught. Okay, so then if you see the first term in all the three equations, so QA is common here. You can take it out, right? So then you are having ln d12 by r, d23 by r, d31 by r. So we are going to add these terms d12, d23, a by r, d31 by r, right? So then log a plus log b plus log c. So log a plus log b plus log c can be written as log abc, right? So by using that, you can write this summation of first terms will be equal to qa ln product of all these d12 by r, d12 by r, then d23 by r, so d23 by r, then d31 by r, d31 by r. Okay, this is the summation of first three terms. In similar way, if you write for summation of this second terms also, so this in all the terms you will be having qb as common. You can take it out. So qb. So now you have to add all these three. So ln a, ln b, ln c. If you use the same equation again here, this can be written as ln r by d12 into r by d23 into r by d31 you will get. Okay, so this will be equal to qb ln r by d12 into r by d23 into r by d31 you will get. Okay, so plus for the third term qc is common, qc. Now summation of all these terms will be ln d23 by d31 into d31 by d12, d12 by d3. So first term is d23 by ln d23 by d31 into second term is d31 by d12. So d31 by d12 into the third term is d12 by d23. So this will be d12 by d23. Okay, so this is how you can write. Okay, so this is the summation of all the three equations, right? So now here if you see d23 and d23 will get cancelled, and d31 will get cancelled, d12 will get cancelled. So that means here we are getting ln 1. So ln 1 will be equal to 0. So this complete term value will be equal to 0. You can eliminate this. Okay, so then this can be written as, so 1 by 3 into 1 by 2 pi epsilon naught into qa ln, so this term, so if you see here d12, d23, d31 whole to the power of r cube, sorry, by r cube you will get, plus qb for the second term r cubed by, so ln r cubed by d12, d23, d31 you will get. Okay, so now this 1 by 3 term you can take it as a power of all these two terms. Okay, then what you will get 1 by 2 pi epsilon, this equation you will get here now 1 by 2 pi epsilon naught, this qa, and for this term we will get whole to the power of 1 by 3, whole to the power of 1 by 3 we will get, then d12, d23, d31 whole to the power of 1 by 3, r cubed whole to the power of 1 by 3 will be r, plus, so then qb ln, for this also you will get whole to the power of 1 by 3. So then this 3 will get cancelled. So you will get r here, r by d12, d23, d31 whole to the power of 1 by 3 you will get. Okay, so this equation we are getting finally from this equation. Okay, so then from this equation what you can write again. Okay, so here this d12, d23, d31, so this whole to the power of 1 by 3. So this total term you can take it as d equivalent. So d equivalent is equal to d12, d23, d31 whole to the power of 1 by 3. Okay, so d equivalent. So equivalent equilateral spacing you can say, right? That value is d12, d23, d31 whole to the power of 1 by 3. So now then this equation can be written as QA ln D equivalent by R plus QB ln R by D. In place of this D equivalent, you can write. So this you are getting here. Okay, this is the value of VAB. Okay, in the similar way, you can write for VAC also. Simply in place of B, you can write C here. Right? So this equation can be written as 2 pi epsilon naught QA ln D equivalent by R plus in place of B here you have to write C. So QC ln R by D equivalent you will get. Okay. So now after this you have to add these two. Okay. So VAB plus VAC. Right. So you need to add this and this. So when you add VAB and VAC, what you will get 1 by 2 epsilon 2 pi epsilon here. This value will be the same. So then, so QA both the terms you are having QA ln D equivalent by R, QA ln D equivalent by R. So you will get QA ln D equivalent by R. Right. So now here ln R by D equivalent, R by D equivalent here both will be the same. So ln R by D equivalent into QB plus QC you will get. Okay. So now for a balanced system, QA plus QB plus QC will be equal to 0. So this from this QB plus QC you can write it as minus QA. So in place of this here, you can write minus QA. Okay. So now this ln by R D equivalent, this can be written as reverse of this, minus of ln D equivalent by R. So this minus again will become plus. So now QA ln D equivalent by R, QA ln D equivalent by R. Right here you are having 2 times QA ln D equivalent by R. Okay. So then 2 plus 1, 3 you will get. So if you sum VAB and VAC, so if you sum the VAB and VAC, you will get 3 QA by 2 pi epsilon naught into ln D equivalent by R. So this equation you will get. Again, you have to remember the balanced 3-phase system voltages in which the per phase voltages VAN, VBN, VCN. VAN, VBN, VCN value will be, VAN is the reference, which is VAN at an angle 0 degrees, and VBN and VCN will be having the same magnitude as VAN. So VAN at an angle minus 20, VAN at an angle minus 240 degrees. Okay. So now if you sum these two, VAB plus VAC. So here VAB is nothing but VAN minus VBN. VAC is nothing but VAN minus VCN. Okay. So in place of this, you can write summation of these. Okay. So then if you derive this, so finally you will get the value of VAB plus VAC will be equal to 3 VAN. So we already derived in the previous slides. Okay. So directly I am writing here. So the VAB plus VAC will be equal to 3 VAN. Right. So now, okay. So here in this equation, instead of VAB plus VAC, you can write 3 VAN. Okay. Now 3 will get cancelled. So VAN is equal to QA by 2 pi epsilon naught ln D equivalent by R. So this is the per phase voltage in a 3-phase asymmetrical transmission line system. Okay. Once you know the potential, you can calculate the capacitance easily. Okay. As VAN is equal to QA by 2 pi epsilon naught ln D equivalent by R. So then the capacitance, which is the per phase capacitance, CAN is equal to QA by VAN. Right. So if you substitute in place of VAN, this value, this QA will get cancelled. So that you will get 2 pi epsilon naught by ln D equivalent by R. Okay. So which is in farads per meter. Now if you convert this ln to logarithmic term to the base 10 and this farad to microfarads and meters to kilometers, so then you will get this equation. Okay. So CAN is equal to 0.04242 by log D equivalent by R, which is in microfarad by kilometer. Okay. Microfarads per kilometer we can say. Okay. So here for solving the problems, you can remember either this equation or this equation. So this equation units are farads per meter. This equation is microfarads per kilometer. Okay. So always remember this equation. It will be simple. Okay. So you can easily convert this farads per meter to per kilometer when you multiply with 1000. Okay. So once you know the CAN, so per phase capacitance, then charging current can be VAN by XC. So JXC you can say. Okay, so XC here, VAN by, so XC here is 1 by J omega CAN. So this will be written as J omega CAN into VAN. So this is the charging current. So which is in amperes per phase per kilometer, right? So if you take this equation per kilometer, right? If you take this equation, you will get per meter. Okay. So this is how you can determine the capacitance of a three-phase unsymmetrical transmission line. Okay. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.